Alright, let's do another cruise and hit some main points related to entropy. First, I got a little example for you of finding the change in entropy of a system. So here we have water melting. The hard part here is just figuring out what is Q, what is the energy that went into or out of the system, and we're not going to use the MCAT equation here, Q equals mc delta T, because there's no change in temperature. We can assume that the water stays at the melting point temperature of water the whole time, so at 0 degrees C. So since the energy here is associated with phase change rather than a change in temperature, we get that energy from just multiplying the mass of our water times the latent heat of fusion. And now we have a value for Q that we can use in the equation for entropy change. But what about temperature? We know what happens at the melting point of water, which is 0 degrees Celsius, but it doesn't make sense to use Celsius degrees when doing math, because specifically here, you can't divide by 0. So we're always going to do math with Kelvin temperatures, and 0 degrees Celsius corresponds with 273 Kelvin. And there's your change in entropy. One thing to note here is that units of entropy are an energy per Kelvin, and this is a positive value for the entropy change because energy is going into our system. One way to think about that to make it make sense is that when energy goes in, there's more molecular motion, and therefore more chaos, more disorder, more entropy. Alright, now I'm going to jump ahead a couple slides, and we're going to look at this. The second law of thermodynamics should tell us why when we mix a hot and a cold thing, energy goes from the hot system to the cold system. So therefore we should find that overall the entropy of the universe increases when we combine a hot thing and a cold thing and they come to thermal equilibrium. So let's say we're going to combine 100 grams of hot water with 100 grams of cold water. We know that energy is going to flow from the hot water to the cold water, and they're both going to end up at 50 degrees. Now, assuming that these two systems of water were well insulated and that no energy escaped to the surroundings or came in, then the change in entropy of the universe with this process is the change of entropy of the hot water plus the change of entropy of the cold water. Now to figure out the energy that went from the hot system, here's where we do use mc delta T because there is a change in temperature. Now, in our example, both of these systems have the same mass, 100 grams. They both have the same specific heat capacity because they're both liquid water. That would be 4.18. And they're both experiencing the same delta T, which is the change of temperature is 50 Celsius for both of these. But the difference between the hot and the cold system is the average temperature at which the energy was exchanged. So the hot system went from 100 to 50, therefore the average temperature it was at while it was losing energy was 75 degrees. But we know that doing math we have to use Kelvin, so let's modify that to be a Kelvin temperature. And for the cold system, the average temperature that it was at while it was gaining heat was right between 0 and 50, which is 25. And here's the other difference, which is the sign of the entropy change. The hot system is losing energy, therefore it's going to be a negative change in entropy, and that's reflected in the fact that this is actually a negative change in temperature. So I've just plugged in the values for mass, specific heat capacity of 4.18, and got the number for MC delta T, which is 20,900. But who cares about these specific numbers? They're boring. The point of all this is to show that for this spontaneous process of heat moving from hot to cold, that the change of entropy in the universe is positive. That if this is a spontaneous process, that entropy should be increasing. And is that what we're going to get? A positive number? Well, it looks like it because our negative number here is smaller than our positive number. And there you have it, a positive value. So it is indeed an increase of entropy that drives the motion of energy from a high temperature thing to a cooler temperature thing. There's a lot of talk about microstates and macrostates, with examples like coin tosses and cards and what's the other thing? Dice. I don't think that's in the slides, but that's another good example actually. Did you know that 7 is the most likely roll because it has the most microstates? You have a 1 and a 6, you have a 2 and a 5, etc. There's lots of different ways to roll a 7. That's why it's more probable. But anyway, this is a physics class. I wanted to look at something physical that involves microstates and macrostates. So let's look at 4 atoms of air, like argon or something, and how they're likely to distribute themselves around 4 quadrants of a room. So the first macrostate is where all 4 atoms are in one corner, and that is not a likely macrostate to find because there's only one microstate that will give you that macrostate. All 4 molecules have to be in that corner. But it is more likely that you'll find 2 molecules in one quadrant and 2 molecules in another, because there's lots of different ways this could happen, kind of like there's lots of different ways you can roll a 7. You could have the black and the red one in the upper left quadrant and the other 2 down below, or you could trade out the blue one for the red one, and you'd still have the same microstate with 2 atoms in each of those 2 quadrants. So if I found all of those microstates, and there's 6 of them, that means that it's 6 times more probable that you're going to find the gas molecules in that microstate number 2. And since there's more microstates associated with macrostate number 2, it means it is a higher entropy macrostate. So therefore it makes sense that if you start with 4 gas atoms in one corner, they're going to disperse because entropy is increasing as that process happens.